지금 이름이 엄혜린인가요? So we learned YOLO algorithm last time, so we will continue. And before proceeding, I had two questions last time, so I will answer that first. And before that, I explained this part, the confidence value. I think, yeah, I wrongly described this in previous lecture. So I said this as 0 or 1 before, right? But yeah, if it, but this is actually not 0 or 1, but these have to have this value, okay? So what does this means is this probability for object is, it should be 0 or 1. If there is object inside the cell, it has to be 1. And if the object is not in that cell, in that grid, then this object probability have to be 0. Okay, I mentioned this as 0 or 1, but what does this means is this is the distance between the ground truth bounding box and the predicted bounding box. This for this, for measuring the distance between two bounding boxes, we normally use IOU measure, and I will explain this first in this slide. So when calculating the distance between two bounding boxes, how they intersect is measured in IOU, and this is IOU because their name is abbreviation for this, intersection over union. Okay. So this is union, the union area for these two bounding boxes, and this is the overlapped regions area, so intersect area for intersection. Okay, this area is intersected region between these two bounding boxes. So this area is called as intersection. So the ratio, if we calculate the intersection over union, then that is actually called IOU. Okay, so this ratio is actually saying that how much these two bounding boxes are intersected. Okay, so it goes close to 1. That it means the intersected region is actually same as the overall region. Okay, so it have to be exactly same. Two bounding box has to be exactly same if their IOU is 1. Okay, and it could be gradually become far, and at this moment, the intersected region becomes 0, and the IOU eventually becomes 0, right? So if intersection over union is 0, it means these two bounding boxes are not intersected. Okay, so it means these two bounding boxes are different. Okay, so we are using this IOU as the measure for the distance between two bounding boxes. Okay. So here, IOU, truth and predict, they are measuring the distance between predicted bounding box and the ground truth bounding box. Okay. So if these two are same, ideally this IOU have to be 1, right? And if these two are not intersected, this value would be 0. Okay. So the confidence value here are actually denoting this part. this part, okay? So not merely 0 or 1. The confidence value have to estimate this value, okay? The probability for object needs, it should be ideally 1. And the IOU, it should be ideally 1. But in practice, this would not be maybe 1, but it would be the value close to 1. But if there is an object, then their value may be close to 1, but not exactly 1. But anyways, we regard the IOU value as the ground truth when this value, the ground truth confidence value, becomes the IOU, the IOU value we just saw, okay? So this confidence value becomes the IOU value between predicted bounding box and the ground truth bounding box. And we are, because it is ground truth, we regard this as just 1, okay? So DC, the confidence value, should predict this value, but this in the ground truth, this value, we can set it as 1, but we calculate the real IOU value between predicted and ground truth boxes and use it as the ground truth, okay? So this part was slightly different from what I mentioned in previous lecture. So, and another thing is, this part are calculated from this part, okay? So when there is object, what would be their class? Is this probability, okay? So, strange. So I cannot, okay, this is deleting all. So this part is from the this vector, right? So for each vector, we will estimate each grid object class, okay? So this part is estimated from this vector, and this part is the confidence value. So that would be obtained from one scalar value from this each bounding box information, okay? And by multiplying them, we can actually use this information in the inference, okay? So this is indicating actually the score for each bounding box. So how much they are intersected with the ground truth and what class they are having, okay? This is the actually used in the inference step. But some students ask me in the last, and at the end of the last class, some students ask me why it becomes like this, okay? I think if you multiply this with this, it should be joint distribution. Okay, not exactly this, right? But we regard these two as same because this object, we will calculate the class index. We will consider the class of the object only when object exists, okay? So normally we have to marginalize out this object to obtain this, right? Mathematically, this is true, right? But yeah, for marginalizing out this, here, when object is, this formula, I will rewrite it like this. Right? So when object does not exist, this is indicating the probability of class when object is not exist. And this is the probability when object exists, okay? But this simply goes zero, okay? When there's no object, the probability, class probability have to be zero, right? So we can regard this is equal to this, right? Because of that, okay? But yeah, anyways, I think, yeah, this formula itself is not, I mean, is false, but there's additional constraint that this is becomes zero when object is not there. We will not count any class probability. So this makes sense. Okay. Anyways, in the inference step, we will use this for, I mean, measuring each bounding box's score. Okay. And another question was this. So in here, in YOLO algorithm, we anyways estimate for each grid, we estimate the probability, and at the same time, we estimate two bounding box locations, okay? One student asked me, some object could be larger than each cell, okay? So if we estimate bounding boxes from each grid, how we can estimate the bounding boxes which is larger than each grid. Okay. So yeah, actually that's good questions, and I found that in paper they are saying this X and Y. So I think I cannot. Anyway, in the top left part, each bounding box contains 5 predictions you can maybe see, right? X, Y, W, H, and confidence, right? But the X and Y coordinates represent the center of the box relative to the bounds of the grid cell, they are saying. So XY is normalized, the coordinate XY is normalized by the cell size, the grid cell size. So XY is indicating where it's located within the grid, okay? But the width and height are predicted relative to the whole image, okay? So width and height, they are, maybe the model will estimate the normalized value, maybe from 0 to 1, but they are actually multiplied with whole images, width and height, okay? So this is what they are saying. So I will explain it again here. So X and Y coordinate, they would be normalized coordinate, but what they are indicating is these cells, they are regarding when they are 0, X is located in this line, okay? And when X is 1, that location is actually indicating this location. And when Y is 0, it is indicating this Y coordinate. And Y is 1, then this that is indicating this coordinate. So, I mean, X and Y here are indicating the coordinate, normalized coordinate inside the cell, okay? So, they are responsible, the grid here is responsible when the object bounding boxes center is located inside each cell, okay? But W and H, they are also 0, having the value from 0 and 1, but they are indicating the relative size compared to the whole image. Okay, so even though their x and y are located inside this grid, but their actual size can be larger than each grid. Okay, are you guys following this? So actually, not sure you are following this, so I will summarize it again. Cannot delete actually. So these values are multiplied with grid widths, right? And multiplied with grid height. That is, this length is grid width, and this is grid height. Okay. So their location is bounded to this grid size, x and y, their center point, but their width and height should be the value between 0 and 1, but they are multiplied with the image width and image height. Okay, so they can represent the boxes which is larger than the grid. Okay. Okay, and the confidence values are indicating this, and this part, it is obtained from this vector. Okay, are you guys understanding this? Okay. So anyway, from each grid, it can predict this kind of bounding boxes. And this is the laws I mentioned. Okay. So this flag was important. Okay, this flag is activated as 1 when there is object inside that grid. Okay, so I is the index for grid. So actually, S is denoting the grid number. So this was set as 7 because we divide the grid as 7 by 7. Right? And B is the bounding box number estimated from each grid. Okay. So when object is inside that grid, we apply these laws. Okay. By enforcing their x and y values close to the ground truth x and y, and also when object is there, the same MSC loss is applied for training the width and height of the bounding box. And also when object is there, we also have to supervise the confidence value as well. Okay. And when there is object, we also have to learn the class probability here as well. Okay. But if there is no object, then our confidence value should become 0. Okay. So this is only loss when there is no object inside the grid, but remaining 4 are applied when there is object in each grid. Okay. And this code was necessary because our ground truth is our training data is actually having some image and some bounding box and class as the ground truth. We have training set like that. So this is image. We have image in our training data, and we have some coordinate value for the bounding box, and also have to have their class. Okay, these are the ground truths. But we have to supervise our network in this format. Okay. So our final network output is 7 by 7 and having this dimensional vector. So we have to somehow transform this information in the same format as our final output and apply these laws afterwards. So this is for making such S by n dimensional array from the original ground truth. Okay? And this is the laws implemented this part. Okay. So you can see here they are making the object needs flag, okay, which was this and this, okay. And you can see afterwards, adaptively, the MSC laws are applied, okay. So you can observe that. And this was the IOU score I mentioned, and this is the code for computing the IOU. So, I mean, from given two bounding box, when calculating the union, we can calculate it like this, area 1. So area 1 is indicating the area for the first bounding box, and the area 2 is indicating the area for second bounding box, and the inter is indicating the intersected regions area. So when calculating this union area, we can add these two and minus the intersected region, okay? So, and also IOU is calculated as intersection over union, okay? So this part is for calculating intersected area and area 1 and 2, okay? So this is code for calculating IOU. And next is for introducing the non-maximal suppression thing. So this is frequently called as NMS, which is the post-processing part. So the initial result of the YOLO, if we visualize it, it has many redundant bounding boxes, but we have to filter out and remain only the best bounding boxes, okay? So that algorithm is actually called as the non-maximal suppression. So actually, these scores are having the list of 98 bounding boxes and having their scores, okay? Actually, scores are decided by this, okay? The IOU score, predicted IOU score multiplied by their class probability. Okay, so actually this score are having that, and this is having the bounding box width and height and X and Y position information, okay? And this threshold is some hyperparameter we have to set, okay? But we will set it as 0.5, but we can vary it later. And anyways, we first sort the scores. So this part is making the top, the bounding box with top score located here, and this here we sorted like to have the bottom, the bounding box index with worst score located here, okay? So this is the sorted list of the bounding box, okay? This is the order variable. And here we iterated this code until the order index is having no element, and we will make the list of the bounding box which we have to keep in this variable keep, okay? And we first insert the highest scored bounding box in the keeping list, and yeah, if we only have one bounding boxes in the list, then we will stop the algorithm. And this part is for calculating the IOU. Okay, we already, this time we will calculate the score for we will calculate the IOU between the topmost bounding box with all other bounding boxes. So because the topmost bounding box, it has the highest score, so we will remain this. We have to remain this, and also at the same time we have to delete all other bounding boxes if they are having much redundancy with this bounding box. Okay, because compared to these bounding boxes having redundancy with this is having the higher score, so we will remove all other bounding boxes which have redundancy with this topmost one. And how we calculate the redundancy is we will actually calculate the IOU between this topmost and all other bounding boxes. And if their threshold is larger than 0.5, we set here, we will actually delete them. Okay. But in the code, what they exactly do is they find the list of the bounding boxes which have smaller threshold. It means they find the list of bounding boxes which is not redundant with this topmost one and make actually the new list here. So anyway, this is the implementation issue. So they will make another order new list again by deleting this part, okay? And they iterate this again using the new list, okay? So in this manner, they can delete the redundant bounding boxes and return only the keeping list, okay? So that's the non-maximal suppression. So for example, these redundant bounding boxes are removed and only the bounding box with higher score is remained. Okay. But the thing is, the YOLO, it is proposed in the CVPR 16 paper, but compared to the two-stage method, it exhibits the, real-time speed, but their performance is slightly less than this two-stage method. And two representative limitation is they have low recall and high localization error, okay? So that may be having many causes, but mostly the authors are thinking that they only predict two bounding boxes. So two bounding boxes for each grid, okay? So the number of bounding boxes, they are relatively less in YOLO. So in YOLO version 2, they somehow wanting to increase the number of bounding boxes. And by that manner, they want to secure, to improve the low recall, and also this localization error is also related to the less number of bounding boxes estimated. So somehow that's also relieved. And also object can have many scales. So for example, in images, there could be large scaled object, and also there could be less sized images. So to capture these two scales, multiple of scale features are required. So that kind of schemes are also considered in YOLO version 2. Okay. So, and later, this was anyway the YOLO algorithm. And from now on, I will explain the YOLO version 2. Okay. So this is kind of the conclusion. So this is the faster RCNN, and this is the fast RCNN, and this is the regional CNN algorithm. Okay, these are two-stage method, and this is the YOLO we just reviewed. Okay, so an x-axis, it is denoting the frame per second. Per second, how many frames are processed is denoted here. So this is actually denoting the speed of the algorithm. If it goes to this direction, it means it is faster algorithm. Okay, and the y-axis is indicating the accuracy. Okay, if it goes higher in y-axis, it means the algorithm is more accurate. Okay, so here we can see from RCNN is slow, okay, and the accuracy is limited, but fast RCNN is faster than RCNN. Okay, it is slightly right in the x-axis, so it means fast RCNN is indeed faster than RCNN. And this is denoting that faster RCNN is faster than fast RCNN. Okay, and as it goes, improved, the accuracy is also improved a lot. Okay, but the YOLO is located here. So this is kind of the line for indicating the real-time needs. Okay. Last time I mentioned that if one algorithm's speed is their FPS is larger than 30, we regard it as the real-time algorithm. So if some algorithm is located right side of this line, that it means the algorithm is real-time algorithm. Okay, this two-stage algorithm, we cannot call them as the real-time algorithm. But anyways, the YOLO, we can call it as the real-time algorithm. Okay, but we can see their accuracies are quite limited. Okay, even compared to RCNN, the accuracy of YOLO is limited. There's gap, but you can see the YOLO version 2, they are real time, and at the same time, almost more accurate or comparable to the accuracy of the faster RCNN. So we will now see how the YOLO version 2 could be improved compared to the YOLO. Okay. But before that, I may have to explain the concept of recall and precision again. So precision is kind of the measure that can measure measure how the model performs good. Okay, this is definitely important measure for measuring the performance of the system. Okay, but recall is also kind of important measure. But previously, when measuring the accuracy, most of algorithms are using this precision for measuring the accuracy. But here, when concentrating on only the precision, the authors are finding that the YOLO eventually have the low recall. So it is also problematic. So after maybe when developing the YOLO version 2, they are considering having higher recalls as well. Okay. Then I will explain what is the difference between this recall and precision. So we can, I mean, so these two measures can be used to evaluate the performance of any system. Okay, so um, we can exemplify two persons maybe. So this person is a talkative person, and we can say this person as the less talkative person. Okay. Then we can say this person say maybe this amount of words every day. We can say like that. Then among these words, maybe only this amount of words are correct. Okay. Let's say in this situation, this person's precisions are very low. Okay. Having very low, less precision. Okay. Because among what she says, very limited number of words are correct. Okay. So she has less precision. But for example, let's say this person, he says only this amount of words every day, but we can say like this amount of words are correct. Okay. Then this person, in terms of precision, he's having the higher precision. Okay. But maybe in terms of truth, I mean, how to say, in real world, maybe there are, let's say, this amount of truth we have to cover, right? Maybe I have to make it more extreme. So let's say this person only say only 100 words every day. And let's say he, among them, only 90 words are correct. But we have to tell maybe this amount of truth, okay? But maybe this person, she may have the chance to tell, to cover all the truth, right? So when we discuss with her, maybe we can reveal all the truths in the world. Okay, there are higher chance when we discuss with her, right? But when we discuss with him, we may have, I mean, less chance to cover all the truths in the world, in the real world, maybe. Okay, so I mean, in terms of precision, this person can have more precision, but I mean, in terms of the record, I mean, this is the measure for the record. So I mean, there are some truths we have to reveal, okay? And the record is actually the measure how much the truth was covered, okay? So number of truths, and here is how much it is the covered truth is the record, okay? And precision is number of words the system say, and number of correct words is the precision, okay? So in terms of precision, this person is high, but it is, I mean, because he say less, there would be less chance to cover all the truths in the world, okay? So, I mean, when measuring the performance of the system, we have to consider this recall as well as the precision. Okay. Okay. Are you guys understanding this recall and precision? Okay. So I mean, YOLO, it predict the less number of bounding box tend to estimate less number of bounding box. So among the estimated bounding box, it can coincide with the ground truth bounding box. So it means the precision is high, but YOLO, it can miss the ground truth bounding box, okay, because their recall is low, okay. So that's the the limitation, one important limitation of the YOLO. So compared to the YOLO, they added multiple schemes to make the YOLO version 2. And YOLO, its performance was like this, but YOLO version 2, their accuracy is becomes higher than original YOLO, okay? And the first method they added is the batch normalization. Actually, this is not the thing proposed in YOLO paper. There at the time of actually the CVPR, the YOLO version 2 is proposed in CVPR's 2017, and in this period, batch normalization was proposed in separate paper, and they just applied this and see that scheme is working good in the object detection pipeline. But I have to maybe explain what's the batch normalization here. So actually this batch normalization is pointing out the covariate shift problem. So we have the deep learning architecture like this, but there would be no criteria to bound the scale of the responses in each layers, okay? So in standard convolutional layers like convolutional neural networks like AlexNet or Google LeNet and VGGNet, we cannot kind of bound the intermediate responses, okay? So these responses may have some distributions like this. Their mean is maybe 0 and their variance is this, maybe, having this kind of distribution in their response. But after this layer, after applying some differentiable layers, they can have the distributions like this, okay? And after this layer, they can have distributions like this, okay? So, I mean, the scale, their responses scale can be varied much during the training, okay? And this problem is actually called as the covariate shift phenomenon, okay? Changes in data distribution for each layer, okay? So when we normalize their scales in the intermediate layers, this paper, the paper that proposes this batch normalization is saying that the training of the convolutional neural network becomes more stable, okay? So they add actually this batch normalization in between these two layers, okay? These are added, okay? And what they do is they normalize their responses by the mean of batches and variance of the batches, okay? So we are during the training, we are using the batch normally, we are using the stochastic gradient descent, which uses batches, the number of multiple images we are using. So we calculate the batches, the mean and variance, their scales. We are considering their scales actually. And actually we make it to standard Gaussian distribution. Okay, we actually subtract mean and divide by their variance. That when the responses are transformed using this formula, then they become to have zero mean and also having one variance. Okay, so by transforming the intermediate responses in this manner, they can remove the effect of the scales in the responses. Okay, they actually can get rid of this covariant shift phenomenon. Okay, so this is the original distribution without the batch normalization, but when applying this batch normalization, all becoming to have zero mean and variance one. So the training of the CNNs become more stable using this batch normalization. So this is what I'm saying, what I said. Okay, so for the batch that they calculate the mean and variance, and we actually normalize the samples here. Okay, but the thing is, during training, we can use batch, which is the multiple images. Okay, during training, we can use batch, but at the testing, one can test just one image, okay? And some other person can use multiple images, maybe 10 or 100 images. And this number of images could be different from the number of images used in the training, okay? So the network is already trained to have the weight that fit to the the batch size. But at the testing, there is slight gap to the number of batches used in the training. Okay, so these values are additionally learned. We cannot get the mean and variance for the samples samely in the training at the testing stage. So we have to learn this additional value to inverse transform the normalized signals to the original scale. Okay, so actually batch normalization have to learn this gamma and beta to apply the inverse transformation regardless of the sample size. Okay, so in the testing, we will not do this mean and variance calculation and doing this normalization because the batch size could be different from that used in the training stage. But instead, we additionally learn this gamma and beta, which can directly do inverse transformation of the samples regardless of their number of images. Okay. Actually, this is one trick used in batch normalization. And anyway, without batch normalization and with batch normalization, the training goes more stable, and the training goes more stable. At the same time, the final accuracy obtained could be better when with batch normalization. Okay. So in here, YOLO version 2, they involve batch normalization and the accuracy becomes better. Okay. And also, they try to use this kind of high resolution classifier and detection. So YOLO version 1, they used, the VGG16 architecture as the backbone So this was the initial the backbone algorithm, and here we estimate S by S n-dimensional array. Okay, but our input was 448 by 448, but their backbone was VGG 16. But you may remember that the original image size for this image classification network, the VGG16 network, was only this size, 224 by 224. But the YOLO, they increased the resolution to 448 by 448 because detection normally requires higher resolution because multiple objects could be inside an image. Okay, in the image classification, I mean, just one object could be there when one main object is inside an image. So the image size could be small, but detection task, multiple objects could be located. And because of that, they actually increases the resolution two times, okay? But this could be harming the performance. So YOLO version 2, actually they fine-tune this VGG16 network of using the image classification data for 10 networks. Okay, so here in YOLO 1, they just replaced the input image size by this. Okay, and then they train from the from the VGG16's ImageNet pre-trained weight, they further fine-tune this object detector using the object detection data. But in YOLO version 2, they increased the image size and also fine-tune this network for 10 epochs using the rescaled image classification data, ImageNet data. They do this first and then fine-tune the fine-tuned network for object detection task. So that's the difference. So that's called as this scheme. And this scheme, simple scheme, can increase the performance a bit here, right? And also, they removed the some of the FC layers, and also they remove the pooling layers, okay, and instead involve more convolutional layers. So the input size now becomes 2 times than the image classification network. Now the image size is this, but the pooling layer, you may remember the pooling layer. If the stride is 2, when the stride is 2, the input would be actually halved if we apply this pooling, okay? But also the convolutional layers, if they have same stride 2, then the image size would be halved, okay? But the thing is, pooling almost do nothing, okay? But they only reduce the image size without doing nothing. But convolutions, they at least apply some filter operation and then anyways transform the images. And if we make their stride as 2, it still reduce the image size, okay? So instead of applying pooling, they try to involve more convolutions because convolutions tend to retain more information, okay? So by replacing the pooling and FC layers into convolutional, their accuracy is becoming less actually. And also they have the anchor boxes as well. So I will explain this part and finish maybe. So anchor boxes, this is important schemes for getting higher result. So as I said, recall is also good, important measure for measuring the performance of the system. Okay, so for increasing the recall, we may have to estimate more bounding boxes. Okay, previously we divide the images into S by S, which was 7 by 7 grid, and for each grid we estimate 2 bounding boxes. Okay, so maybe the number of bounding boxes are only 98 in YOLO version 1, right? But here in YOLO version 2, what they do is uh, they actually not use this grid, but they use the intermediate feature map. So compared to the original image, the feature maps are 32 times reduced. Okay, so they tend to get this 13 by 13 feature map. And for each pixel of the feature map, they estimate 5 bounding boxes. So this time, 13 by 13 by 5, which is almost 1,000 number of bounding boxes are estimated in YOLO version 2. Okay, so this is important difference to YOLO version 1. But I mean, if you see the accuracy, which is the precision, when using this convolutional operation and anchor boxes, you can actually see their precision was reduced. Okay, but they are saying when using these anchor boxes, they can increase the recall. Okay, because they estimate more bounding boxes compared to YOLO. So their precisions could become less because they tell more, right? But their recall is now becoming better. They are becoming more, having more chance to cover all the truth inside the image, okay? So that's the important change in YOLO version 2. And also, when using these anchor boxes, I just said that the input to YOLO was 448 by 448, but their dimension, the width and height, are actually changed to 416 by 416. This is, the authors are saying that the feature maps are this amount reduced compared to the original image. So when reducing this, they can obtain 14 by 14 feature map, okay? But they prefer odd number of width and height because they just want one center in the feature map. But if you use this even number of width and height, there is no center pixel here. Okay, so, but the objects are tend to located in the center positions in images. So they prefer to use the odd number of feature map. So they on purpose change the width and height of the input images. Okay. So yeah. So by involving these two, the precision becomes less, but their recall is actually 7% improved. Okay. So there becomes room to further improve the algorithm. And for later part, I will maybe continue from next class. Okay. Okay. So this is the important changes appeared in the YOLO version 2. Okay. Okay, thank you. Let's see you next Monday. 혹시 출석 안 하신 분 나와서 해주세요.